graph should look the same as mine. So we should all end up right now at this same point, where you have all your points plotted. And then you have two colors on there. So one color connects each of the members of a family, and the other color connects each of the members of a period. So look at your period. Do you have a periodic table next to you? All right. Take a look. You might, on yours, you might have run out of room. I taped an extra little bit of graph paper on mine, so if you ran out of room on yours for those last couple points, that's okay. Yeah, probably, right? All right, so look at your periodic table. Find lithium. Find sodium, potassium, rubidium, cesium. Where are they on the periodic table relative to each other? They're all in the same column. Remember, columns go up and down because columns hold up buildings, so columns go up and down. So they're all in the same column. What do we call elements that are all in the same column? Families, or sometimes groups. Mostly I use the word families, but you'll sometimes see the word group. Find beryllium on your periodic table. Magnesium. Calcium. Strontium. Barium. Where are they relative to each other? They're all in the same family. So you should have one color on your graph connecting all the points for the same family. And then you can go all the way down the boron, carbon, so boron family, carbon family, nitrogen family, oxygen, fluorine, and across. So make sure all those lines are connected with one color. The other color. Find lithium again. Then beryllium, boron, carbon, nitrogen, oxygen, fluorine. Where are they on the periodic table relative to each other? They're all in the same row. So what do we call it on the periodic table when elements are in the same row? They're members of the same period. So you should have the other color connecting members of the same period. The other color connecting members of the same period. I have also labeled on here, too much extra talking though, because then I can't hear what I'm doing. I have also labeled on here, I have labeled some of the specific families, which we're going to go over today. So lithium, sodium, potassium, rubidium, and cesium. That's a specific family called alkali metals. Beryllium, magnesium, calcium, strontium, barium. That's a specific family called alkaline earth metals. And then fluorine, chlorine, bromine, iodine, that's a specific family called the halogens. We're going to go over some of those specifically named families today. Now, let's look at the alkaline metals then. Look at these ones. Remember that the y-axis is the radius, so that's how we're measuring the size. So as you go down the family, from lithium to sodium, potassium, rubidium, cesium, what happens to the size of the atom or the radius?
It's bigger.
It gets bigger. So as you go down the family, the radius or the size gets bigger. So we can find somewhere on your sheet where you can write that summary statement. So the atomic radius or the size increases as you go down a family. Atomic radius or size increases as you go down a family. Okay, what about across a period? So if you look at lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, you're going from left to right across a period. What's happening to the radius or the size as you go left to right across a period? It gets smaller. It gets smaller. So the atomic radius or the size of the atom, it decreases as you go across a period. If you go left to right across a period, the atomic radius or the size of the atom decreases. It gets smaller. In a minute. Yeah, I can scoot it back up in a minute. Why do you think that these trends happen? Because why? Because it feels like it. Let's talk about a family first, because I think that one's a little bit easier to understand. So if you go down a family, if you look at your Bohr model sheet, look at the number of electron shells as you go down a family. Each time you go down down one element down that family, there's one more electron shell. Well, does it make sense that the atom would get bigger if there's more electrons and therefore more electron shells? You got more layers there, right? So that makes sense that as you go down a family, you're adding more electron shells, you're adding on more layers, more energy levels, so that atom's going to get bigger. Okay, how about across a period, though? This one's a little bit trickier. So if you go left to right across a period, the atom gets smaller. Do you have any guesses why that might be? Because it just wants to?
Yeah.
Any guesses? Guesses are good.
Does the word get smaller? I don't know.
Righty, tighty, lefty, loosey. If it's left, then it's wait.
If it's left,
Actually, that might be a good way to think about it. Righty tighty, lefty loosey. Okay, because here's why. Let's look at lithium to fluorine, or sodium to chlorine. It's going to be the same. How many valence electrons does lithium have? How many valence electrons does lithium have? So it has 3 electrons total, so 2 are going in the first shell. So how many valence electrons?
No, I'm so high. Oh my god.
How many valence electrons? 1. So lithium has 1 valence electron. How many valence electrons does fluorine have?
2.
It has a total of 9, right?
Wait, fluorine? Wait, where's that?
Fluorine, F,
Fluorine.
has a total of 9, which means 2 go in the first shell. 2 go in the first shell, and then 7 go in the valence shell. So lithium has 1 valence electron. Fluorine has 7 valence electrons. If fluorine has 7 valence electrons, what does it want to do?
Get another one.
It wants to gain 1, so it has a full valence shell, so it has that octet. So if it is so close it only wants to gain 1 more, how badly do you think it wants to gain that 1?
So bad.
So bad. So how tightly is it going to hold on to the 7 it already has?
What did you say?
Really, really, really tight. That if it already has 7 and only wants 1 more, the 7 it already has, it's going to hold on to it really, really, really tight. Lithium, though, if it has 1 valence electron, what does it want to do?
Let it go.
It wants to lose that 1 valence electron. So if it has 1 valence electron, that outer shell right there is not held very tight. It's just kind of out there because it's going to be easy. It's not going to take a lot of energy to lose that 1 electron. But if it has 7 valence electrons, it really wants that extra 1, and it's going to hold on to the 7 that it has really, really, really tight. Which means an atom with 7 valence electrons is going to have a tighter, it's going to hold everything closer and tighter than with only 1 valence electron. So that's why it gets smaller as you increase valence electrons as you go from left to right across the period. Okay, so any questions on, oh wait, I want to show you this though, and then we're going to switch gears over to the note, I mean not really switch gears.
Righty, tighty, lefty, loosey.
Yeah, because if it's on the right, it has more valence electrons, so it holds it tight.
Dude, I'm so.
If it has 1 valence electron on the left-hand side, it's holding it really loosely. Righty, tighty, lefty, loosey, you're right.
Dang, I'm smart.
Look at that. Or you just got lucky.
No, I'm smart.
Or both.
It was definitely lost.
Or both.
Righty, tighty, lefty, loosey. I
Okay.
got five.
Hey, down here in the corner, see this little tiny outline of the periodic table that I have?
Yeah.
Well, as you go down, this is just a visual way of thinking about it. As you go down the family, the atom gets bigger. What does this kind of look like?
A circle.
A what?
It looks like we have like Minecraft. It's like this.
Yo!
How about a snowman? I was thinking snowman.
Oh, this is I thought you actually meant the actual.
No, not the periodic table, just that part. Snowman? If you stand though, Jake, if you stand, you need to make sure that you're not being disruptive to anybody else. Also, I'm absolutely thrilled that you guys are more responsive than first hour because they just kind of stared at me all hour. However, if you are talking when I'm talking, when I don't need you to talk, then we're not going to get through what we need to get through. Okay? Okay, so does this look like a snowman? Kind of. I don't know if this is like officially called the snowman rule or this is just what I heard sometime, but it works either way. So as you go down a family, the atoms get larger. If a snowman tips over on its side, it looks like this. Well, as you go across a period, the atoms get smaller. It's kind of like a snowman standing up and a snowman that fell over. So if that's helpful, you might want to draw that into your graph somewhere, just some little spot. And then we're going to switch over to our notebooks. What?
It's Olaf, but in the summer.
There you go. All right, switching over to notebooks. Actually, switching over to vocab sheet real quick first. We're going to add in family/group and period. Add these two to your vocab sheet. Family/group and period. Yeah, I got that somewhere. So add these two right here, these two onto your vocab list, and we'll be added into our notebook on Monday.
Don't have it unless it, oh my gosh. What's the definition again?
What's a family?
Up and down. Something that
It's all, it's all the elements that are in the same column on the periodic table. What's a period?
Same row.
The elements that are in the same row on the periodic table.
I honestly did not hear it.
Family and period. Add family and period to your vocab sheet. Nope, two separate ones. Family/group is one term, and period is another term.
I wasn't listening. What does family mean?
You tell me, you know what it means. What does family mean? There you go. Yep, all the elements that are in the same column on the periodic table. Yeah. And period is all the elements that are in the same row on the periodic table. Yeah, but don't be a pest. All right, and then when you've got that down on your vocab sheet, and then we're going to switch over into the notebook. We're going to look at a couple of trends on the periodic table. So what do we know based on where things are on the periodic table? Okay. That works. Yes? Not right now. Ask when Kyla comes back.
Of course, Kyle's going to be drinking half a.
Yep. Yeah. Okay, so what we're going to do is we're going to be looking at a couple different trends on the periodic table. Atomic radius we just talked about, but we're going to add it into our notebook here. So what happens, so what happens as we go down the family? What happens to the radius? Kelsey? It gets bigger. So as we go down a family, radius increases. As we go down a family, radius increases. Why? Because there's more valence shells. Then across a period, from left to right, radius decreases left to right. Why? Because the more valence electrons held tighter, which makes a smaller atom. Okay, now we're gonna draw on here wherever the biggest atom is and wherever the smallest atom is. We could just draw circles for atoms, but that's kind of boring. And this kind of looks like a castle to me, like across the top, you know? So we're gonna draw princesses instead. Yep. All right. So, where in this castle, in which corner of this castle would the biggest, knowing the trends, would the biggest princess live?
Or fat.
No, just biggest.
I'm hearing fat.
She's like a giant princess.
Oh, to the right. Yeah, I'm lighting up the heck.
Where, Kelsey?
The left bottom corner.
The lower left. The biggest princess.
Oh, she holds down the castle. I got you.
The biggest princess.
Yeah, it's actually on the second
That
block.
looks like
She's
a
smart.
stick person, not a princess.
Hey. Here's her curly hair.
She a
The biggest princess lives down in the lower left corner. Because atomic radius increases as you go down the family, but it decreases as you go left to right across a period. That's her princess hat.
Oh.
I thought princesses get crowns or tiaras.
This one gets a hat. You can draw a crown if you want.
Okay.
Oh yeah, Kyle.
Where does the smallest princess live?
I'm drawing a stick.
Top left. Top right.
Top right, because radius increases as you go down, so it's got to be at the top. And radius decreases as it gets smaller as you go from left to right. So the smallest princess
Why are my glasses?
She interested.
My drawing skills is just
lives up there.
I'm seeing interested.
That's the smallest princess.
Do you know what like a cheeseburger is or no?
You're not being helpful right now.
I'm sorry.
Yeah, Kyle.
What does that even say?
Smallest princess.
Oh.
All right, so we got a quick note on size there. Next thing we're going to look at is the different regions of the periodic table as far as metals, nonmetals, and metalloids. So let's do the next part. Yep, smallest is in the top right.
Metals plus what?
Metals and nonmetals.
Oh.
Metals and nonmetals. Yep, we're going to end up like with 4 of them, I think. We're also going to add in here this part right here. Part that comes from right there.
I gotta draw a whole nother table.
Hey, why is this part right here? Why does this come out and down like that?
Because it can't fit.
Yeah, like, so look at the ones of my magnets on the sideboard over there. See how those ones are actually all put in the one row? These ones, this part right here though, on most periodic tables, they're actually kind of like taken out and removed, like a little like subsection there. But that would be, right there, that would be where they fit, and you can see what that looks like on the sideboard over there with my magnet periodic table. That's why those are there. Okay, who knows where the non-metals are on the periodic table? Jacob?
Kinda like, can I point?
No.
I don't know where, like.
Sure, you could also use words like left or right or top or bottom.
Just gonna go up here. Like right here.
You just kind of, what? Where?
Like right here.
Nope, non-metals.
Oh,
Non-metals.
right here.
So non-metals are going to be,
I thought we were talking about metals.
nope, non-metals are going to be kind of along the right side and especially the, well, far right,
Oh.
like that. So those are the non-metals. Those are the non-metals. Raise your hand, please, and tell me one thing you know about non-metals. Kyle?
What's the fluorescent thing you watch, or like neon color, neon thing you watch?
So the noble gases like neon, we can put electricity through them and they light up in certain colors. Good. Kelsey? They're not good conductors, right? Yep. Anything else you know about non-metals? What state of matter do they tend to be at room temperature? Most of them are gases. Yep. Mostly gases at room temp. Emily?
Maybe really high in temperature? No. Or not.
Well, I mean, at room temperature, they tend to be gases, and if you made them hotter, they'd still be gases.
Yeah.
Yep. Okay. How about the metal? Oh, hang on a second. Wait a minute. Right? The hydrogen is also a non-metal. I always forget about that over there. Look at the one that I've drawn on the board right behind me. See how hydrogen there is kind of like floating above the rest of it? Sometimes I'll see periodic tables like that. And that makes a little more sense to me because hydrogen, like, yes, it sort of belongs over there because of the characteristics that it has, and the same with these guys. But it also kind of sort of doesn't fit over there. So sometimes when I'll see them, and they'll kind of be drawn where the hydrogen is like floating above, and that makes a lot of sense to me. Okay, now we have the metals. These are all the metals.
That's a lot.
That's a lot. Yes, you're absolutely right. It's a lot. Most of the periodic table are metals. That's a good thing to remember. Most of the periodic table is metals. Raising your hand, who can give me a characteristic of metals? Kylie.
Conductors?
A lot of them are good conductors. Yeah. Sawyer, do you have another one?
Solid.
Most of them are solid at room temp. Yep. Kyle?
If you heat them up, you become a liquid.
And so most of them are solid at room temperature, which means if you would get them hotter, at some point they would melt and go from a solid to a liquid. What are these metals in the middle called?
Expensive metals.
What are these metals in the middle called?
Dude, I don't remember.
Look at your periodic table then, they're labeled on there.
What does it say? It just gives me a color. I don't know.
Transition metals. Those ones in the middle, they're transition metals. They tend to be good conductors. You'll notice that copper is there. Well, we use copper for a lot of conducting sorts of things. They tend to be shiny. They tend to be not as reactive as some of the metals over here. They tend to be more stable. They tend to be, what else? Shiny, good conductors, not as reactive as some of the other metals. All right, list without calling it out. I'm going to call on you. Give me an example of a transition metal. Jasmine, look at your periodic table. Give me an example of a transition metal.
Like the word?
Yeah, yep, an element name.
I thought she pointed at you.
Which one?
71. I don't even know how to say that.
I'm looking for it.
71's on
Oh, lanthanum? That would actually be one of these down here, which we call intertransition metals.
Oh.
And those ones down there, many of them tend to be radioactive, which means that the balance, their nucleus is not very stable as far as the balance between protons and neutrons, so they tend to fall apart. Your nucleus will fall apart, and that's what we call radioactivity. Okay, Ano, can you name a transition metal? Yep, that's a good one. Sawyer, I want you to name a transition metal that we're super familiar with.
Gold.
Gold, absolutely, good. Emily?
Copper.
Copper, good, that's another one we're super familiar with. Okay, last part we're gonna put on this one. What do we call these ones that are in the middle, that have some characteristics of metals and some characteristics of non-metals? What do we call these? What?
Lloyd?
Yeah, metalloids.
Oh.
They have some characteristics of metal, some characteristics of non-metal. Silicon would be a good example of a metalloid.
They use that for like spoons or something.
For spoons?
Like like the ones you use like for like mixing stuff. Like not like actual.
Oh yeah, yeah. Yep, you could have like a silicon spatula.
Yeah.
Yep, absolutely.
Oh.
Okay, I'm gonna turn the page.
What is the blue one called?
Metalloids. All right, ready for me to turn the page? Turn the page. Okay, the next one, we're going to be looking at number of valence electrons by family. And the ion charge. So we're going to need to separate out our 8 major families here. So I've got my periodic table drawn. Here's the first one, and that has hydrogen at the top, and then lithium. And then the next one starts with beryllium. We're going to skip the transition metals because some of those get a little bit goofy and don't quite follow the rules that we've learned so far. So the next one then starts with boron. We might have to get kind of skinny here on mine. And then carbon. And then nitrogen. Yeah, you might need to extend yours if you're going to run out of space. And then oxygen, fluorine, and you've got helium, and I'm going to add on neon there so at least we have that whole second period.
Do they all have to be at the top, the ones that are over?
What do you mean, like the labels?
Yeah, like that. Do they all have to be up here?
Yes, yeah, because you want to follow the shape of the periodic table. And this is all the second period across here.
No.
No, Jacob, no. We're gonna be able to use this on our toast, right?
Yep.
No, Jacob.
Okay.
What about vocab?
Vocab sheet, no.
Oh.
So you need to know those.
Have the answers.
Yep. All right, so how many valence, we're going to go through valence electrons first. Jacob,
What?
why don't you turn your body so you're facing more toward me than the boys, the rest of the boys.
I'll hurt my back.
Turn your body. That's better, thank you. Okay, how many valence electrons does hydrogen and lithium in that family have? How many valence electrons? One. So we're just going to label across the top here. Valence electrons, there's 1 for that family. What about how many valence electrons for the family that starts with beryllium?
2.
Good job. How many valence electrons for the family that starts with boron? How many?
13, I don't know.
Nope.
No?
How many valence
3.
electrons? 3.
Oh.
That's 3 on top. Or 3 on top.
Why 3? Because I'm smart.
Do you remember, maybe last week, maybe the week before, we talked a little bit about carbon? We drew that one. How many valence electrons did carbon have?
That's right.
Yeah, 4. And then we talked about how since it has 4, it's too many to gain or lose. So what it does instead is it shares electrons. And it forms something called a covalent bond, which we'll talk about in the next 2 weeks sometime. How many valence electrons does nitrogen have? And the rest of the ones in that family?
5, 6, 7.
5 for nitrogen.
Or 6, 7, 8.
How many valence electrons does oxygen have and the rest of it in its family? 6. And for fluorine, and the rest of it's in its family? 7. How about these guys over here?
8.
So for the most of them, 8. Helium is that exception to that because it has a full valence shell with 2. But you know, that's the exception that kind of proves the rule. So in general, they have 8 valence electrons. So what kind of ion are they each going to form then? If lithium has 1 valence electron, what does it want to do with that 1?
Get rid of this negative bond.
It wants to get rid of 1 negative charge, which means it's going to have 1 more positive than negative, so it's going to form an ion of +1. Beryllium has 2 valence electrons. What does it want to do?
Get rid of it.
Keep 'em.
It wants to get rid of the 2 valence electrons, which means it's going to have 2 more positive charges than negative, so it's going to have a charge of +2.
So if you want 8, if you want 8, like you want 8 on the electron, what if that's 4? Would it lose 4 or gain 4?
It would, so that's that carbon example, where carbon, what it's going to do is it's actually going to share electrons.
Share, okay.
Yep, that's called covalent bonding, and we're going to get into that in the next 2 weeks.
Okay, thank you.
That's not on the test, right?
Not on the test. Not yet.
Test are like 5 questions.
The one that you have tomorrow is 1 page back and front. Most of it's multiple choice, some of it's not.
Okay.
All right, what about boron? If it has 3 valence electrons, what does it want to do?
Get rid of them.
It's going to get rid of those 3, so it drops down to the next shell, which means it has 3 more positive, it lost 3 negative charges, which means it has 3 more positive charges than negative, so it's going to form an ion with a charge of +3.
Oh. So this is +4, +5, +6, +7.
The carbon family is not, since it has 4, that's what we just talked about, is not going to gain or lose electrons. It's going to share, so it's not going to form an ion.
So 0.
So nothing. We're not going to put anything under there. If nitrogen has 5 valence electrons, what's easiest for it to do?
Get 3 at 1.
To gain 3 electrons, and then it would get its octet.
So is it negative?
So if it's going to gain 3 negative charges, yep, you're right. It's going to have a charge of -3. It's going to gain 3 more negative charges than positive.
Oh, I see the pattern.
See a pattern? Good. Chemistry is all about patterns.
Is that a -3 or +3?
That's a -3 right there. Okay, oxygen has 6 valence electrons. So what does it want to do to get its octet? Gain 2 negative charges, gain 2 electrons. So if it has 2 more negative charges than positive, it's going to have a charge of -2. The ion is. And what about fluorine? It has 7 valence electrons. So what does it want to do?
Negative 12.
Get 1.
It wants to get 1 negative charge, get 1 electron, which means it's going to have 1 more negative charge than positive. So what's its charge going to be? Yep, a -1. Helium, neon, argon, krypton, xenon, radon. What's their deal?
Noble gases.
They already have their full valence shell. They already have an octet. So they're not going to form an ion. Oops, ready for me to move down yet or no? Okay. We are moving right along. This is the last one now. This one we're going to look at special families. Yep.
Kyle, you got that everywhere. Yes, you
Oh, that was kind of goofy looking. All right. So we're going to look at 4 families here that we're going to give specific names to. A family in general refers to any group of elements that are in the same column, but we're going to look at 4 specifically. Why does a family matter? What's the deal about a family? What can you know if 2 things are in the same family?
They're in a group and they're on the way down and they
Yep.
go up by like 8 or 9 or no, never mind.
So yep, they're in the same column in the periodic table. Are they gonna have the same number of valence electrons?
Yeah.
Yeah, so if we look at like up where we had up here, like lithium, sodium, potassium, rubidium, cesium, all of those ones, they're gonna have 1 valence electron. They're gonna form an ion that's +1. So every family member has the same number of valence electrons, which means they're going to have similar characteristics. They're going to behave the same, and they're going to have similar reactivities. So every family member has the same number of valence electrons, which is why they behave or react similarly, why they have so many of the same characteristics. Jacob?
I go to the bathroom.
Yeah. All right, so we're going to name 4 of them. First one right here is called the alkali metals. This is called the alkali metals.
Even hydrogen?
No.
So cut that one out.
Yeah.
Okay.
Alkali metals. So what do we know about alkali metals? Is their number of valence electrons important?
No. Yes. Yes.
Yeah, because that determines how reactive they are. So they have 1 valence electron. They only have 1 valence electron. They really badly want to get rid of that one, which means they're super reactive. Remember seeing the video of sodium? Yeah, so what happens to sodium when you throw it in water? It explodes, yeah. Okay, so they're the most reactive of all the metals. They also kind of showed how he cut off a piece of that. They're silvery in color, but they're really soft. So you like sodium, you can cut that with a butter knife. So they are soft and silvery. And they form ionic bonds with nonmetals. So ionic bonds, that's what, again, we're going to talk about bonding the next couple of weeks. That means that they form ions and then form a bond with other ions. So they form ionic bonds with nonmetals. So the ones that are all the way over here. This is like weird and goofy. A lot of this should be reviewed from the choice notes that you just did, those periodic table trend choice notes. Good. So a lot of these terms should be like, oh yeah, that's right, I read about that. So then what is the next family called? Anybody know? Jaden? Not yet. Those come next. Those are in the middle right here.
Are they middleweight?
So before, nope, not metalloids. Those are over here.
Normonophil.
So we're looking for the name of just the family for this one. Ano? Alkaline earth metals. Alkaline, ALKALINE, earth metals. Alkaline earth metals.
What color is that?
Jaden, do you know how many valence electrons these ones have? Yeah, they have 2 valence electrons. So yeah, they want to lose those, but they're not quite as close to that octet as the alkali metals, which means they're not going to be quite as reactive. So they are a little less reactive, a little more stable, less reactive than alkali metals. They're also harder, stronger, denser than alkali metals. Of these, maybe you've seen like magnesium ribbon, which is like a solid magnesium metal, where like, yeah, you can, I mean, it's a really thin piece and you can bend it, but it's not like sodium is almost like cream cheese. I mean, not that soft, but sodium is really soft. Those alkali metals are really soft. The alkaline earth metals are harder, denser, stronger than compared to the alkali metals. All right, 2 more. Let's finish them up. Well, 2 more families to add. This is the last little periodic table. This is the last piece section that we're doing. 2 more families though. What's the name of the family that starts with fluorine? Anybody know? What?
Maltoids, something like that?
Nope.
Non-cardinals?
No. Halogens. Halogens.
I like you're just reading your vocabulary.
Well, I'm not, I'm reading off the periodic table.
Halogens. I don't know, how many valence electrons do they have? 7 valence electrons. So they really, really, really badly, they're so close to that octet, they really badly want 1 more, which means they're going to be very reactive. So they're the most reactive of the non-metals. Look at some of the examples of metalloids. Fluorine, chlorine, bromine, iodine. Have you ever had surgery where they had to like cut through your skin and then after you wake up when you're done you notice that it's stained yellow around that incision?
Is that iodine?
That's iodine. So where's iodine? What family is it?
It's with fluorine 1.
Yeah, so it's a halogen. What about chlorine? Why do you put chlorine in a pool of water?
So it stays clean, no bacteria gets in.
Yep. So one of the uses that we are familiar with some of these halogens is that they're used to sterilize or kill germs. Those are just 2 examples of that. All right, and last family here. What do we call them? What do we call them? Noble gases. Good job. How many valence electrons do they have?
8.
Yeah, all of them, right? They have a full valence shell. So they already have they have full valence shell. Are they going to do anything?
No.
No, they're not going to react with anybody. There's a word here, inert, which means they are not reactive. Excuse me. Thank you. And they are pretty much odorless, colorless gases. Until, like Kyle said, we put electricity through them and then we get neon lights, or argon lights, or helium lights. We tend to call them all neon lights, but the different ones we get different colors from. All right, yeah, right? I know, that's a really long talking day. The last thing that we need to do, your vocab sheet. I want you to add these 4 family names to your vocab sheet. Alkali metals, alkaline earth. This is your tool, right? And it's going to be useful to you if you have definitions down on there. Alkali metals, alkaline earth metals, halogens, noble gases.